It's pretty amazing when you stop and think about it. How much of our world just runs on repeat? The sun coming up and going down, the seasons changing, the tides. Nature is just packed with these incredible rhythms and cycles. And the really cool part? We can actually teach a computer to see, understand, and even simulate these very same patterns. So, let's dive in and see how we can do just that. I mean, seriously, think about it. From something as huge as the Earth's yearly trip around the sun, all the way down to the steady tick-tock of a clock, repetition is just a fundamental part of, well, everything. And in the world of programming, we have a fantastic way to capture this rhythm. We use something called a loop. So, that's the big question, right? How do we take this elegant, natural repetition and translate it into a language a computer can actually understand? How do we build these rhythms right into our code?
Well, we do it with this incredibly powerful tool called a loop. And we're going to start with the real workhorse of the bunch, the for loop. Honestly, think of this as your #1 tool for mastering repetition in code.
Okay, so the easiest way to wrap your head around a for loop is to imagine you have a collection of items, like a list. The loop just, well, it steps through that list, one item at a time, and does something with each one. It's kind of like taking a box of photos and looking at each one individually until you've seen them all.
All right, let's see a real example. Here we've got a Python list with the different phases of a cell's life cycle. Now look at that code, 4-phase in cell_cycle. It's almost like plain English, isn't it? For every phase inside our cell_cycle list, print it out. And boom, look at the output. It just walks right through the list and prints each one in order. Simple, clean, and totally predictable. Okay, that's cool for lists we already have. But what if you don't? What if you just need to do something a specific number of times? Like simulating a planet making 10 trips around the sun? For that, we need a way to create a sequence of numbers on the fly. And that, my friends, is where the range function comes in. This thing is a game changer. It's an unbelievably handy tool that just generates a sequence of numbers for you exactly when you need it. You just tell it where to start and where to stop. It's the absolute perfect partner for a for loop when all you need to do is count. And here's a perfect example. To simulate 10 years, we write for year in range 1, 11. Now pay close attention here because this is the one thing that trips everybody up at first. The range function starts at the first number, which is 1, but it runs up to but not including the last number. So range of 1, 11 actually gives you the numbers 1 through 10. Once you get that little quirk, you're golden. And as you can see, the output prints a line for every single one of those years. All right, your turn. A little pop quiz. Based on what we just said, how would you tweak this code to simulate the planet's orbits starting from year 5 and going all the way to year 15? Take a second and think about it. What numbers would you need to put inside that range function? So, did you figure it out? The answer is range 5, 16. Right? We want to start at 5, and to make sure the loop includes year 15, our stop value has to be 1 higher, so 16. That's the trick. And once you master that one little detail, you have total control over your loops. Okay, so far so good. But let's be real. Patterns in nature are often a little more complex than just a single list. A lot of the time, you have cycles that happen inside of other cycles, like months within a year or hours within a day. So how do we model that? Well, we use something called nested loops. This is just the perfect way to think about it. A nested loop is literally a loop inside of another loop. Imagine the seasons as the big outer loop. For every one pass of the season loop, a whole inner loop of months has to run its full course. The big loop just waits patiently until the little one is all done before it moves on. That's the whole idea right there. Cycles within cycles. And here's what that looks like in actual Python code. See that? The outer loop goes through the seasons. The first time through, it hits summer and prints that out. But then it pauses. And the inner loop completely takes over, printing a line for month 1, month 2, and month 3. Only then, after that inner loop is finished, does the outer loop finally wake up and move on to monsoon. It's just a really powerful way to model these kinds of layered patterns. All right, so we've used loops to model biology, we've used them to model astronomy. Now let's bring it all home and apply this to a classic physics calculation. This is where you'll really see why loops are absolutely essential for any kind of scientific computing. This is what I'm talking about. This is where loops really shine, automating repetitive calculations. Here, we want to figure out the potential energy of an object at a bunch of different heights. Now, we could write out that mass times g times h formula 5 separate times, but why would we? That's just asking for a typo. Instead, we just toss the heights into a list and let a for loop do all the heavy lifting. For every single height, the loop does the math and prints the result. It's efficient, it's clean, and it's way less error-prone.
And this brings us full circle, right back to where we started. Whether it's the intricate branching in the veins of a leaf, the perfect geometry of a spider web, or even the physical laws that govern the universe, it's all about patterns. In a way, patterns are the fundamental language of everything around us.
And the really amazing part is, with a tool as straightforward as a for loop, you now have the power to describe those patterns, to model them, to explore them for yourself. So I guess that just leaves one question. What patterns in your world are you going to program next?